Hello everyone. Welcome to this training session on Actuarial Common Entrance Test ASET. As a part of this session, we are looking at the subject on mathematical foundations. And today we are going to cover the chapter called vectors. In fact, as a part of the curriculum, we have vectors and matrices together. But as a part of this session, let's look at only the vectors per se and try to do some of the most commonly possible numerical problems as far as the vectors are concerned. Okay, let's get started. So, the key things that we discuss in this is what is a vector and how do you represent that? How do you add the vectors, subtract the vectors, multiply the vector with a scalar, or how do you find out the scalar product of the vector? Or for that matter, what is meant by the magnitude and the angle between the vectors. These are some of the things that we would be discussing. So let's get started into it. Right. So just to the first thing which we are like trying to look at is what actually is a vector. Any quantity which is being represented either in the two-dimensional space, okay, at a point. Let's say I want to represent this particular point, which is having a magnitude as well as a direction in the positive x-axis. So there is a magnitude as well as a direction. Any particular quantity which is having both a magnitude as well as a direction, we call that to be a vector. The most common thing which we do is, if we want to represent any point either in the two-dimensional space, this being an x-axis, this being a y-axis, or even the three-dimensional space, probably I create one z-axis also. This is the way we represent the three-dimensional stuff. X-axis, y-axis or z-axis. In these three directions, if I want to represent a quantity, that is where we resort to the vector based notation. The most common form of a notation for a vector is the IJK form. So whatever is the distance on the x-axis, distance from the x-axis is what it is being looked at with respect to I. Y-axis it is looked at with respect to j, and z-axis with respect to k. But yes, it's not just limited to the three dimensions. You can extend it to n dimensions also. But because we generally deal either with a two-dimension or a three-dimension kind of a space, we talk about the IJK notation to a large extent. Otherwise, if I'm only talking about two dimensions, it would be in the form of I and J itself. So let's say I want to talk about a vector, let's say like this, I plus 2j plus 3k. It means it is present in 3. So the point for it in the three-dimensional space is nothing but 1, 2, 3. So 1 on the x-axis, 2 on the y-axis, and probably 3 on the z-axis. So based on this, this particular point gets represented. The other way you can very well represent this vector is in the matrix form. The typical matrix form, the same. What the way we can write the vector is as a column vector, something like this, 1, 2, 3. If I write it like this also means I plus 2j plus 3k. This is one more notation. Or so generally it is written in the form of a one single column, 1, 2, 3. Sometimes for some other calculation requirement, people write it as a transposed matrix. So it's nothing but it is written in the horizontal row form, but with a transpose symbol at the top. So, which is nothing but this is same as this in the matrix notation. In the matrices chapter, we'll talk about these things. These two remain the same. And in fact, in turn, this gets worked out to this itself. So, I plus 2j plus 3k, they are represented in any of these notations. So, when I write something of this, let's say just for example, 2, 5, minus 3. So negative quantities also could very well be there. So it is nothing but it means 2i plus 5j minus 3k. That's it. Right? So this remains the same. So your vector can have, this is nothing but it is 2 units on the x-axis, 5 units on the y-axis and minus 3 units on the z-axis. So that is what is the meaning of this particular representation. So if you try to understand it in a two-dimensional space, you can visualize it in the three-dimensional space itself. So it means, okay, 2 units on the x-axis, 5 units on the y-axis and probably minus 3 units on the z-axis. This is what is the three-dimensional representation of your matrix. Now, from an exam standpoint, the most common areas which we need to be comfortable with are the addition of two or more vectors. For example, I talk about one vector in the matrix notation 1, 2, 3. And I take another vector probably 4, 5, 6. Let's say these are the two vectors I am talking about, which is nothing but this is I plus 2j plus 3k. And this becomes 4i plus 5j plus 6k. That's the only difference. So when I talk about that these are the two vectors and I simply have to add them, the process is very simple. Add all the i's separately, all the j's separately, all the k's separately, which is all x-axis components separately, y-axis components separately and the z-axis components separately. So 5, 7 and 9. So this is the addition between two or more vectors. Similarly, when we talk about the subtraction between the two vectors, that's also the same. 1, 2, 3. And again, let's say another vector I have 4, 5, 6. If I have to do a subtraction between the two, it's again 1 on 1 subtraction. So 1 minus 1, 1 minus 4 minus 3, 2 minus 5 minus 3, 3 minus 6 minus 3. So it is nothing but minus 3i minus 3j minus 3k. And there is also a scenario of, let's say I want to find out for this itself, this vector 1, 2, 3, you multiply it by 3, which is nothing but each element you multiply by 3. This is a scalar multiplication. Multiply a vector by a scalar. This is the kind of a solution which we are going to get. 3 multiplied by 1, 3 multiplied by 2, 3 multiplied by 3. And there could be some kind of complex calculations also. Let's say this is a vector A, this is a vector B. Let's say the question could very well be on find out 2A minus B, 2A minus 3B. Okay, the process is the same, 2A. So this means this is 2, 3B, 12. So 2 minus 12, minus 10. Again, 2A, 4, 3B, 15. 4 minus 15, minus 11. Similarly here, 2A, 6, 3B, 18. 6 minus 18, minus 12. So this becomes 2a minus 3b. Whatever may be the calculation we are talking of, as far as the addition is concerned or the subtraction is concerned or multiplication by a scalar is concerned, is a straightforward stuff. So these are some of the things that you may have to be comfortable as far as our exam is concerned. Right, so just getting a basic understanding into these things will definitely provide a value addition for you. Then every vector has what we call as a magnitude. Another important point you need to be comfortable with is the magnitude of a vector, which is nothing but the length of the vector, which is represented by mod A or sometimes just by a simple A. A means modulus of A, which is nothing but the length, which is nothing but, let's say if I have a vector like I plus 2j plus 3k, the magnitude of it is nothing but just like your extended Pythagoras theorem. All the values 1 squared plus 2 squared, the j's coefficient plus 3 squared, the k's coefficient, which is giving me square root of 14 is the magnitude of this particular vector. Let's say I want to talk about the vector is given to me in some kind of matrix form like this 3, 5 and minus 3. Then the magnitude of it is nothing but square root of 3 squared plus 5 squared plus minus 3 squared. Minus 3 squared again is 3 squared itself. Right? Doesn't no difference between a minus 3 and a 3 as far as squaring is concerned. 9 plus 9, 60, 18 plus 25, 43. Now another vector, 4, 5, 6. Square root of 4 squared plus 5 squared plus 6 squared. 36, 61 and 16, 77. So these are the ways you find out the magnitude, and which is nothing but the length of that particular vector from the origin. Origin is, let's say I want to define the three-dimensional space, right? This is the origin. Let's say my point is somewhere here in a three-dimensional space. I want to find the distance of this particular point. That is what we are calling as the length of that particular vector or the magnitude of that vector, and we are finding it using the square root of the i's coefficient square plus j's coefficient square plus k's coefficient square. And using this information, I can find out what is called as a unit vector. Unit vector is nothing but the vector whose magnitude is 1. Any vector whose magnitude is 1 is what we call as the unit vector. So how do I convert any existing vector into a unit vector? Straightforward. You take the vector as it is 4, 5, 6 and you multiply that with a scalar which is nothing but 1 by its magnitude. You multiply that vector with a scalar which is nothing but 1 by its magnitude. Magnitude is root 14. You take, which is nothing but, this is 1 by root 14, 2 by root 14 and 3 by root 14. This is my new vector, which is the unit vector. Now try finding out the magnitude of this vector. It will give me equal to 1 itself. So any unit vector is nothing but that particular vector whose magnitude is equal to 1. So we should be comfortable doing these kind of calculations also in our exam. So when a vector is given and we are asked to find out the unit vector corresponding to it, it's a straightforward work wherein you take the vector as it is and multiply it with a scalar which is equal to 1 by the magnitude of that particular vector. Alright. So let's move on to our next concept in this context, which is called as the scalar product of two vectors. So we have multiplied the vectors with a scalar, but there is a possibility that I can multiply two vectors itself. So let's say one vector 1, 2, 3, another vector 4, 5, 6. There are two different ways of multiplying these two vectors. When I multiply these two, there are two methods of multiplication. One is called as a vector product and the other one is called as the scalar product. The two vectors can be multiplied in two different ways. One is called as a scalar product, the other one is called as a vector product. The vector product is also called as cross product, whereas scalar product is also called as dot product. But just to reduce your confusion, as far as AZ is concerned, we are not bothered about the vector product. We only look at the scalar product or the dot product between the two vectors. The calculation is only the scalar product or the dot product between the two vectors. So this is how the process which we do to find out the scalar product. A is represented typically using A dot B. The scalar product is represented using A dot B, which means this is here also I can put A dot B. That is what is called as a scalar product. And there are two ways of determining it. One is you just multiply the the x-axis values with the corresponding x-axis values, the j's component with the j's, k with the k, and then add it up, sum product. So which is nothing but 1 into 4, 4, plus 2 into 5, 10, plus 3 into 6, 18. 28 plus 4, 32 is the scalar product of these two vectors. So the answer will be a simple plain number. It's no more a vector. In the scalar product, the answer will not come out as a vector again, it's a scalar. That's the reason why we call it as a scalar product. Scalar product is nothing but the product of these two vectors, which is a simple scalar quantity. So you will have only a number, you will not have it as a vector at all. So 32 is a simple number. There is another, so A dot B in this case is 32. So theoretically it should be equal to another scenario which is equal to AB cos theta. A is nothing but magnitude of vector A. We know the magnitude of vector A is square root of 14, which we have already found it out earlier. Square root of 1 squared plus 2 squared plus 3 squared. The magnitude of vector A is square root of 14. Magnitude of vector B is square root of 77. 4 squared plus 5 squared plus 6 squared. Right? 36 plus 25, 61 plus 16, 77. AB cos theta, where theta is the angle between these two vectors. The angle between these two vectors is theta. So, in this example, we know that 32 equal to square root of 14 into square root of 77 into cos theta. From here, I can find out cos theta. Cos theta equal to 32 divided by square root of 14 into square root of 77. So, into 77. I need to find out the square root of that. So this is the square root and I divide it by 32 and I do a 1 by. And so the cos theta is coming out to almost 0.974. So from here I should be able to find out theta, which is nothing but the cos inverse of 0.974. So in some of your calculators you can find the cos theta directly, cos inverse directly. So you can simply find out cos inverse 0.974 and you can find out the value of that from your cos tables. You can very well find out your cos inverse value. So that is the angle between the two vectors. So one from the scalar product you can find out the angle between the two vectors also using this kind of a mechanism. right? So one thing we need to be comfortable as concepts is you can find out the scalar product between the two vectors just by multiplying their corresponding coefficients and adding that up. And couple of important things that we need to understand here. Yes, now that we are able to find cos theta, if probably cos theta comes up to 0, how does cos theta come up to 0? Only when a dot b equal to 0. So probably if I create something like this, let's see here, 1, 2, 3, right? And probably if I create like this, minus 19 to 5. Now you try to find out a dot b here. 1 into minus 19 plus 4 plus 15, 0. If a dot b is 0, then obviously cos theta will be 0. If cos theta is 0, based from the basic values of cos theta, theta will become 90 degrees. 90 degrees means these two vectors are perpendicular to each other. So I plus 2j plus 3k is perpendicular to minus 19i plus 2j plus 5k. These two vectors are perpendicular to each other because a dot b equal to 0. And if a dot b, or probably a dot b is same as ab, then cos theta will become equal to 1. Cos theta equal to 1 means theta equal to 0 degrees. 0 degrees means both the vectors are parallel. Right? Both the vectors are parallel, then it becomes cos theta equal to 1. Both the vectors are parallel. So these are some of the important outcomes that we need to be comfortable with. And any perpendicular vectors are also called as orthogonal vectors. So again, as a terminology you need to be comfortable with. Whenever you find that two vectors are perpendicular or the angle between the two vectors is equal to 90 degrees, we call those vectors as orthogonal vectors. Alright. So as far as the vectors is concerned, this is what is the basic context that is there as a part of this chapter. As a part of the ACET exam, these are the concepts that we need to be comfortable with. I hope you got a decent amount of awareness on the various calculations related to vectors. If you have any further queries, you can feel free to give me a call on the number 98480 You can even send me an email mentioning the doubt which you have so that I can respond back to that on this email ID which is mentioned here, vamsidhar@facegurus.com. I request you to visit my website www.facegurus.com for any further clarifications, updates in the training and consulting areas in the areas of finance, investments, statistics, analytics, and actuarial sciences using tools like Excel, VBA, and SPSS. Thanks a lot for listening to this session. Thank you very much.